Okay, so today I wanted to talk about a math problem from my stats class and talk about, I guess, like how to do it, some steps, some cool things about it, and then some other kind of connections that can be made about it. So the question is, there are N people at a party, they're all wearing a different hat, and so they all throw their hats in the center. All the hats are randomly mixed up, and then each person just grabs a random hat. So the question is, what's the probability that none of the men select their own hat? Um, so think, how would you calculate that, right? Because you can kind of get lost because you could say, well, each person has a 1/n chance of grabbing their hat. If you add those all up, you get to one. But obviously, there are scenarios where multiple people get their own hat, and there are scenarios where nobody gets their own hat. So, like, when I kind of think about these problems, the first thing I like to do is, instead of n, if we change that to 2, right? So two people mix up their hats. What's the chance that nobody gets their hat? Well, we have person A and person B, right? And so there are two options. Either person A gets person's A hat, they get their own hat, and B gets their own hat, or they don't. So what is the probability that none of the people get their own hat? Well, in this case, that would be here. So it would be 1/2. So if the question was for two people, we know the answer would be 1/2. Now, what if we had three people? There are 6 options. We have A, B, C, A, C, B, B, A, C. So the blue letter is which hat they grab, and the black letter is that designated person. So we're going through each of the 6 scenarios. So situations where nobody gets their own hat. Well, in these two, A gets his hat. In this situation, C gets their hat. Here, this works because nobody gets their hat. This works because nobody gets their hat. And here, B gets his own hat. I could circle all of them, but kind of the point remains the same, that there are 2 situations here where nobody gets their hat. So 1/3. Yeah. B, C, A. Good. So now when we try to generalize this, we need to think about the probabilities and how they go, and think about each scenario, right? So kind of the first thing we need to talk about here is inclusion, exclusion. So the probability that nobody gets their hat. So this is for scenario 2. So A, this is the region in which person A gets their hat. This is the region where person B gets their hat. So if we want to find all the outside space, what we can do is we can take 1, like 100%, and we can subtract this whole figure. Now, how do we find the probability of this whole figure? Well, what we can do is we can do 1 minus the blue region, so probability A, and minus probability B. But then we have to add, we double subtracted this area. So we have to do plus probability of A union B, or intersection B. This might make more sense. So we're subtracting B. We're subtracting B. But then the shaded area we double subtract, so we have to add it back in. This part. Now for 3 people, this gets complicated because to find this total space, we add all of A. So we add this whole thing. Let me choose a different color. So we add all of A, and we add all of B, and we add all of C. But then we double count these regions. We double count the purple region, the orange region, and the pink region, and we triple count the pink region. So here to find to find A union B union C, to find that area, we add A, we add B, we add C, and then we have to subtract A union B, subtract A intersect B, sorry, A intersect C, and B intersect C. But then we have to add this region because we subtracted it 3 times and we count for it 3 times. So we haven't counted it essentially. So we have to add back in this intersection. So why this pertains to the problem is that each event is not mutually exclusive, as we saw for AB. We can't say there's a 50% chance that A gets their hat and a 50% chance that B gets their hat, because if A gets their hat, then B has to get their hat. So we can't count the events independently. But what we can do with n people is construct a Venn diagram with n circles, and we can add and subtract the parts that we overcount to find the probability that at least one person gets their hat, and then do 1 minus that to find the probability that nobody gets their hat. So in this example, this orange region would be the probability that A gets their hat, C gets their hat, and B does not get their hat. This pink region would be the probability that they all get their hat. So if we can construct a diagram like this, or really just know the formula, then we can do 1 minus the total area of that figure to find the probability that nobody gets their hat. So if we look at n equals 2 again, if we look at specifically, or let's start at 1. So let's look at n. So n being 1, where one person gets their hat. So using this before, we can find all the situations where somebody gets their hat, where one person gets their hat. So if there's 3 people, we know there's a 1/3 chance that A gets their hat, 1/3 chance that B gets their hat, and 1/3 chance that C gets their hat. As like seen through this, all the options. There's in 2 of the 6, A gets their hat, in 2 of the 6, B gets their hat, and in 2 of the 6, C gets their hat. So that would be akin to this first row. And then we subtract all the scenarios where 2 people get their hat, aka these 3. And then we add back in the scenario where they all get their own hat. So inclusion, exclusion, you alternate between adding and subtracting, adding, subtracting. So if there were 4 circles, we would add all of the just single circles, then we'd subtract the intersections between 2 different circles, then we'd add the triple intersections, and we subtract the 4th intersections. That's inclusion, exclusion. So that's what we're essentially trying to do here, is we're trying to find all the probabilities where one person gets their hat. We say EI, basically just the probability that all the sums of all the probabilities where one person gets their hat, and then we subtract that where 2 people get their hat, and some where 3 people get their hat, and so on and so on. So if we look at just one person getting their hat, we can take for n, so there's n people. So the chance that any given person gets their hat is 1 over n. And then there are n people. So we have 1. And this is what's a confusing part of this problem, is if we look at the Venn diagram, the total Venn diagram of A plus B is going to be 1. I mentioned they're not mutually exclusive before, but if we look at each individual person, if there's 2 people, A has a hat 50% chance of getting their hat, and B has 50% chance of getting their hat. So if we add those up, we get to 1. Same with 3 people. A has a 1/3 chance of getting their hat. B has a 1/3 chance of getting their hat. C has a 1/3 chance of getting their hat. We add them up, we get to 1. But that's not including for the overcounting and the undercounting. So now if we found, we want to find where N is 2, where 2 people get their own hat. So that would be this region for 2 people, or these 3 regions for 3 people. So how do we count that? So we count the number of sections there are plus the probability of that section happening. So with 2, there's 1 section. There's just this section with 2 people. And the probability of that happening would be 1/2 times 1/2. A gets their hat, B gets their hat. For in the Venn diagram with 3 people, there are 3 sections. And so if we find the probability of each section, we can multiply that by 3 to get the probability of those spaces. More accurately, we're finding this section, and this section, and then we're going to have to subtract the middle section. So if we have N people, 2 people getting their hat, well, how many sections are there? And then what's the probability of each individual section? So each individual section, we'll start with that first. We have 1/n of the first person getting their hat. And then we have 1/n minus 1 for the second person getting their hat. So there's N people. The probability that A gets their hat is 1/n, as we discussed before. But now if we look at person B, we know that person A got their hat. So there's N minus 1 hats to pick from. So the probability that person B gets their hat is 1/n minus 1. This is done because everything's symmetric. It doesn't matter who person A is, who person B is, but one person grabbing their own hat is going to be 1 over the total number of people. And then the next person grabbing their hat is 1 divided by N minus 1, because we have already taken 1 hat out of the pool. So that's the size of each segment. How many segments are there? So there are a few ways to think about this. The easy way is just it's N choose 2, right? We have N number of people and we're choosing 2 of them to get their hat. Now, what does that mean? How can we think about it? We can also think about it as just N times N minus 1. There are N number of people we can choose to get their hat. We can choose person A, choose person B, all the way down. So that's how many options we have to choose the first person that gets their hat. Now, the second person can be anybody else except for the first person. So if this person is A, if person A gets their hat, person B, C, D, E, all the way to infinity, all the way to N can get their hat, except for person A. Now, if this person was person B, same thing, person A can get it, person C can get it, person D, all the way down. So the fancy way of saying that is N choose 2. We have N number of people and we're choosing 2 of them to get their hat. So these things are equivalent. So we can multiply all this through. Sorry, we also need to divide by 2 factorial here, because we have A and then B. If we choose person A to pick their hat first and then person B, that's the same as choosing B and then A. And the reason we do the factorial is if we have 3 people, we have all these options. So all of these options result in them choosing their hat. It's just 3 different ways of who we pick first to grab their hat, who we pick second to grab their hat, and who we pick third to grab their hat. So we have to divide by the factorial of the number of people we're choosing. So when we do that and divide this through, we'll see that we get 1/2 factorial. We notice that these and these are the same, so we're just left with the 2 factorial. So right now, our answer is 1, and then we're subtracting 1/2. And then we need to keep adding and subtracting and adding and subtracting. We notice 1/2 is the answer we got previously when we just chose 2 people, which is interesting. So now we need to go to 3 people. So by the same logic we used before, we need to find the probability of each section, and then multiply it by how many sections there are in this n number of circle Venn diagram. So the first person is 1/n. Now we've taken that hat out of the pool, so the chance that the second person grabs their own hat is n minus 1. Now the third person, there's 2 hats out of the pool. So we have 1/n minus 2. And then the number of sections is n choose 3. We have n number of people we can choose. We choose 3 of them. So written out in another way, we would have this. The same reason above. It doesn't matter if we choose person A, then B, then C, or A, then C, then B, or B, then A, then C, and so on and so forth. We're still choosing 3 people, and it doesn't matter what order we choose the people to pick their hat. And this simplifies to n times 1/n minus 1, 1/n minus 2 times n factorial times 3 factorial times n minus 3 factorial, which after simplifying, we're going to get 1/3 factorial, which is also 1/6. So here, I chose nobody getting their hat. Right now, these are the sections of people choosing their hat. So we have 1 minus 1/2 plus 1/6, which is 2/3. So 2/3 is the chance that of 3 people, somebody chooses their hat. So when we're finally answering the question, we actually have to do 1 minus 2/3, which gets us 1/3, which is what we see here. So we can do this all the way from 3 all the way to n. So what if 18 people get their hat? What if 27 people get their hat? We can go through the same motions. What we end up with, though, is this interesting pattern of these factorials. So we end up getting 1 minus 1/2 factorial plus 1/3 factorial minus 1/4 factorial plus plus 1/n factorial. So this is the probability that somebody chooses their hat. As mentioned before, in order to find all the empty space, we need to do 1 minus all of the space within the Venn diagram. So this is the space within the Venn diagram. Now we want to find when nobody gets their hat, which would be 1 minus this space. And that, if we notice, it's just a sign flip. So this is equal to 1/2 factorial minus 1/3 factorial plus 1/4 factorial minus that. And this actually brings us to an interesting answer of 1/e, or e to the -1, which I believe is about 0.37. So, and this drops off really quickly. We see it's between 1/3 and 1/2. So once we get to 6 or 7 people, the odds that nobody gets their hat is the same. And I think another way to kind of think about this is if there's 10 people, really loosely, there's a 1/10 chance that each individual person will pick their chance, but there's 10 people. If there's 20 people, you have a 1/20th chance to grab your hat, but there's 20 people. So the chances of any select person grabbing their hat get smaller and smaller, but because there's more people, you have more opportunities to do so. So as we go on, we might say, well, what is E doing here, right? Why do we have 1/E? Why is it E over -1? And this can be seen through like Maclaurin series and derivatives, which is kind of a connection. It's different from stats. It is more found in calculus. So in calculus, we know that E to the X. I'm going to actually do it first and then see the connection. So E to the X, We know e to the x as like population growth rate. We know that the growth of e to the x is proportional to the population. So we see this with interest rate. We see this with population growth. Um, when the growth is proportional to how many people we have, that's the same as saying that the rate of change is related to the amount you have. So we want to find what e to the x is. Like, what is this equal to? Well, if we know that e to the x, its derivative is itself or proportional to itself, we know e to the x is special where it's exactly itself. So let's just say we have f of x, some function, and then we have f prime x, the derivative of that function. So let's just start with some random function. Let's start with 1. What's the derivative of 1? We have 0. Now we want these two to be the same. So what do we do to f prime of x? Let's say that's 1, and let's work backwards. So now what's f of x? F of x would be x plus 1. Well, now we run into the same issue. We have this x that's not accounted for on the right side. So we need x plus 1 here. How do we get to x plus 1? We have x squared over 2 plus x plus 1. But now we have a problem where this term isn't on the right side. We want these two sides to be equal, because if f of x equals f prime of x, then we know the growth is proportional to the population. And I chose 1, so it would work out to be e to the x. But you could start with any constant. If you start with any like polynomial, you'll end up with some function if you work with it to work on both sides. So we have e squared, x squared over 2 plus x plus 1. But now we need to have an x cubed, because how do we get to this term? Is through x cubed over 6 plus x squared over 2. And then if we do it once more, now we're noticing a pattern, I would hope. If we look at these terms, we can see that this is the same as x to the 4th over 4 factorial. This is the same as x cubed over 3 factorial. This is the same as x squared. I forgot an x here. The same as x squared over 2 factorial. And then we have plus x plus 1. So if we go on forever and we keep adding terms to the left side, we're going to end up with 1 plus x squared over 2 factorial plus dot 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 plus x to the n over n factorial. And this is exactly equal to e to the x. So we kind of learn, at least I learned like this Taylor series just by brute forcing the memorization, but it's actually pretty easy to derive, because we think, all right, we need some function. When we take its derivative, we take its integral, we're going to get the same value back. So if we start with 1, well, if we take the integral of 1, then we have x. And if we take the integral of x, we have x squared over 2 factorial. If we take that integral, we get x cubed over 3 factorial, just from the power rule. And then we can do that forever. And then eventually the two sides, as we go to infinity, we'll see that they are the same. So we know that e to the x is 1 plus x squared over 2 factorial. And then, a cool thing you can do is you can just plug in a number for x. So if we plug in e to the 1, we'll get 1 plus 1 plus 1/2 plus 1/6 plus, and this will get us to e, which is 2.7181, I believe. Now, what if we plug in e to the -1? We will get 1 minus, or we can just say plus -1 plus -1 squared over 2 factorial. plus -1 cubed over 3 factorial. And we can keep going. So we'll see e to the -1 is 1 minus 1 plus 1/2 minus 1/6 plus dot dot dot. So we notice we have this alternating pattern of sums and minuses. And if we look at our final answer here, we'll notice that's the same thing we get here. So we have this alternating series of 1 over n factorial, which we can see through the Maclaurin series of e to the x is exactly what you get when you put in e raised to the -1st power. So I think this is a really cool problem. I think it's cool, like if you have really anything more than like 10 people in a room, I mean, you can do this for yourself, so you're at a party, but if you have 10 or more people in the room and randomly mix hats, randomly mix name tags, anything, the chances that nobody will get the thing, their own hat, their own item they used is close to 1/3. It's 1 over e. It's the same thing if you address a bunch of envelopes and write a bunch of letters and the letters in the envelopes mixed up. And so you just randomly put letters in envelopes. The envelopes are already addressed to people. The letters are already written to a specific person. You can rest assured that about 2/3 of the time, at least one person will receive their correct letter in their correct envelope. And then about 37% of the time, nobody will get their corresponding letter envelope that it was supposed to be given to them. I think it's cool that once you get to a certain point, it doesn't really matter how many people you have. You're going to get closer and closer to this 1 over e, but you're not going to get much closer. So here's a quick table. I just searched this out real quickly. For n number of people, the chances that nobody gets their hat. As we can see, I would say right when you get to 5, but really right when you get to 6 people, it is extremely, extremely close to when you have an infinite amount of people or any number of people between 6 and 8 billion people around with their hat. The chances are roughly the same. To 3 digits, it's the same chance that nobody will get their hat, which I just think is really cool and a really cool phenomenon and can be solved through math. So yeah, if you did this experiment 3 times, you would expect one time nobody to get their hat once you 6 more people, which I think is really cool. So yeah, that's what I wanted to talk about in this mini lecture. Yeah, bye.